Okay, so now let's take on a little bit of a different spin on all of this. Now, we could say right here in this integral that we can use a direct substitution, but we need to sometimes use what we call a change of variables, and that is essentially what we've been doing, although we haven't been calling that. If I had the antiderivative of the quantity square root of 3x plus 2 dx, I can certainly make the substitution right here that u is equal to 3x plus 2, and that therefore if we take the derivative of u with respect to x, we're going to get 3 dx. What we've been doing has been called a change of variables, in as much as in this particular step, in order to get dx by itself, we've had to rewrite the expression as 1/3 of du equal to dx. And so to finish off this particular problem, the antiderivative is going to be 1/3 of the antiderivative of u to the 1/2 power du. And so we'll end up with an antiderivative of 1/3 times, let's see, 1/2 plus 1 is 3/2. We've got 1 over 3/2, so we've got 2/3 of u to the 3/2 power plus a constant. So now we go back and we replace our variable and simplify this expression to note that we have 2/9 this time of the square root of u, which is 3x plus 2, raised to the third power plus a constant. Well, that's pretty straightforward, right? We can certainly see how all that's going to work, but let's contrast it to another problem like this one. Well, in this case, we could state let u equal 4x minus 5, but this time we got a little bit of a problem. Do you see it? Well, right away we're going to run into the problem that du is equal to 4 times dx, which would mean that we'd have to have 1/4 of du equal to dx to make this work. The trouble? X. What do we do with that? This is where we use our change of variable right here. Because we've got this extra term hanging out, and it is kind of related to u right here, when we say a change of variable, what we really mean is that we're going to say, well, what would happen if I had an extra x in this expression? Well, we can make the following replacement. U plus 5 is going to equal 4x if we added 5 to both sides of that equation. And of course, that's the same thing as saying 1/4 of the quantity u plus 5 is exactly equal to x. So what we're going to do right here is that we're going to use this replacement here in our antiderivative, so that we're going to see an expression that now looks like the following. 1/4 of the quantity u plus 5 multiplied by u to the 1/2 multiplied by, in this case, 1/4 of du. Now, we can simplify this expression a little bit. For example, we've got 2 factors of 1/4, which are going to come out of this expression as 1/16. And we're going to have to take the integral of u to the 5th, u plus 5 times u to the 1/2. And this looks like a job for algebraic distribution, right? Multiplying u to the 1/2 to both of these terms in parentheses to give us a new expression, which is going to look like 1/16 the integral of u to the 3/2 plus 5 times u to the 1/2 du. All right, so now we've got an interesting expression that we can take an integral of fairly quickly here. Let me go back to my pen. That 1/2 didn't look too good. There we go, 1/2, leaky pen. All right, so what does this come out to be? 1/16 is going to be multiplied by the expression u to the 3/2. 3/2 plus 1 would be 5/2, so we're going to get 2/5 of u to the 5 halves in the first term. And we're adding to that 5 times u to the 1 half. 1 half plus 1 is 3 halves. So it's 5 times 2/3 u to the 3 halves. We just saw that expression in the last example. Plus our constant c. And so the rest of this is all a bit of simplification right here. If we multiply through, of course, 1/16 times 2/5 is going to be the same thing as 1/40. And that's going to be multiplied by our quantity 4x minus 5, which was u, to the 5 halves power, added to, let's see, we're going to get 16 divides into 8 times, so 8 times 3 is 24. We're going to have 5 over 24 of the quantity 4x minus 5, this time to the 3 halves power, plus our constant of integration. And at this point, we can leave this, or we can rewrite it using radicals. Let's go ahead and leave this right now, and we'll say we're happy with that.